So this video is in two parts, and this is the start of the second part of the video on how to implement an LRU cache in constant time in Go. What we've done so far is implemented the requirements for the LRU cache in tests. And what we're going to do now is to actually implement the LRU cache in constant time, so that no matter how large the cache grows, performance does not degrade. So we'll pick it up here as we begin to define and implement the LRU cache itself. So, the very first thing that we should do is add this linked list. So we know that we're going to have the list, which is going to be of type list.list. I think I have documentation here for linked lists. Containing list. It says in the standard library of Go's. A brilliant little library. Never actually used it before. I just looked at the documentation, but it looks absolutely perfect. So let's add this here. So we have our linked list. At the front of the linked list, remember as in our diagram here, at the front of our linked list is going to be the most recently used. At the back is the least recently used. So that means that as things are used, we put them back to the front. And that happens first at the set. But remember that we want to keep this in constant time. So when we have our, when we have our map here, and we look up, what we're doing at the moment is we look up our value in here, like our value, we find it, and we return it. But what we want to do now, instead of just returning the value, we want to point to the corresponding node in the linked list. We don't have to go through the whole linked list to find the node that corresponds to the map. Instead, we want our map, which we access in constant time, to give us the node that we're then going to use to reorder. Okay, so when I set Belgium into here, so let's say I set, it doesn't let me do it. When I set Belgium into this map, it's actually going to point me to the element in the node which represents Belgium. And when we use Belgium, that means that when we shuffle the order, put it at the front. And therefore we can access the element in this list in constant time. And this is what I was talking about with this being such an interesting problem, because we really combine two data structures to get the best of both worlds. We get constant time access using a map via a key, and that gives us constant access time to a list, which allows us to maintain an order without having to scan through every single element in this list to find the one that we want. Okay, so this is the beauty of kind of this solution, is that we combine the two data structures to maintain constant time working with a list. That plus the added performance benefit that we're not going to have to, with the array, move all of these around every time we have to reorder things. We can just change the pointers. So in order to do that, instead of this being a map of strings, we want this to be a map of pointers to list elements. We want the map to point to our element. And I should change that here to a list element. Okay, that's to a node. So now, when we set our element, what we want to do is we want to check whether the element already exists. Okay, and we do that by going l.key. And the reason we need to do this is because if it doesn't exist, if it's not already in the cache, we need to add a new element into the list. So we'll say c.l, and it has, I think, if we look at the documentation here, to push a new element to the front of the list. Where is it? Push front, yeah. So insert new element at the front of the list, which is what we want to do, right? Because when we have a new element, we're setting it for the first time, it goes to the front of the list because it's obviously the most recently used. So we'll call l. That's not so well named, is it? Let's change this to L should be C, say for cache, just for clarity. So let's say, yeah, c.m. Okay, what's this complaining about? Yeah, we don't need this, sorry. Yeah, so if the element isn't already in, then we want to push to the front our new value. Okay, so we just pass our value here, it pushes the element and it returns it to us. And we then want to add it into the map. Okay, yeah, we want to, no, that's a pointer, that should be fine. Yeah, so we want to add it to the map. So if the element isn't already in there when we're setting it, we are going to create a new element, put it at the front of the list, most recently used, and then add that element to the map so that we can retrieve it instantly. Now, if it is already in the map, so this value is already existent in the cache, then we're just changing the value. So we don't actually have a test for this. So perhaps we could have one maybe here where we say, let's just make this 2 just for safety. Up here, you know, if I you know, there's a revolution in the United Kingdom and we make Manchester, one of my favourite cities, the new capital, and then we get the value again. Now we should successfully, sorry, Manchester. We should basically just make sure that we are actually setting that new value, okay? So yeah, that's what we're doing here. So in here, if the value already exists, I think we already have L, we've retrieved it here, and we can just say L value is value. We can just overwrite it. And remember, yes, we still, because when we're setting this, either way, we need to move this to the front. Now we don't want to push it to the front because it's not a new element. So we want to move to the front. So if you, let me see, move to front, yeah, there you go. So then all that's going to do is exactly what we described here, where we change the pointers around. So if I want to move this element to the front, I delete this and just point it here. And then if I move this out a bit, now this no longer points here, it just points to the previous front. That's all that move to front is doing. Okay, and then we don't need this. Okay, so that's the set. If it doesn't exist, put it at the front. If it does exist, just update the value and push it back to the front. And then the get is a fairly similar principle. We want to look it up in the cache because we're trying to retrieve it. If it doesn't exist, then we want to return just an empty string. And if it does exist, then we want to move it to the front because remember, a get should still update it as the most recently used, putting it to the front. And then we want to return the value. And the value is generic here, it's an empty interface, but we want to return a string. Normally, what you should do for type safety is you check that the cast to a string is okay, like this, to avoid a panic. But we know, we can be confident here, we're the only ones setting the map, and it's always a string, so we can just go straight ahead and cast it. If this was running in production, you wouldn't do that, but in this case, we can be very confident it'll be fine. Okay, so that's the first part, which is that we're maintaining, what we're doing is we're maintaining this order. So now the most recent should always be at the front, the least recent will always propagate to the back of the queue in the cache. But what we're not doing is the actual removal part. So the important part of the least recently used cache is the least recently used element is removed so that we maintain that capacity. And you'll remember that we're setting the capacity here. So what we can do here is the capacity will only ever be exceeded if we set a new element. Okay, so what we could do is just here, we can do a set check. So we can, this is the only place where we're adding a new element. So at this point, we can check the length of the list like this. And we can say if it's greater than the capacity, then we want to remove it, remove the last element from the list. Okay, so the least recent user at the back, there's actually a method in the list to give us the one at the back. So I can just call remove from the back, and that should remove it. And now if I just run this on the right hand side, first I'll just run this one. We should still have implemented this cache. Looks like we did. Let's run this and okay. Yeah, so what we are hoping to see was that like the UK would be removed, as it should be with this, when we exceed. So when we put in Belgium, we exceed the capacity of 3, it should be removed. But it wasn't, so I'm not sure why, but let's check here. Is this being hit? Just run this till we get to Belgium. Oh, test failed, why? Let me run this again. Okay, so we're going to set it. We're going to hopefully remove it. Yep, okay, so it has been removed. Yet, when it comes to the get here, we get an OK. You seem to get that pointer to an element which has London. So of course we're using two data structures, and it exists in both. This element is pointed to from the map and it is ordered via the list. Now we've removed it from the list, but we haven't removed it from the map. So what we still need to do here is remove it from the map as well as the list. So the back element is this one. We want to remove the back element. We don't. So the problem with this design is that we don't actually have the key, so we have no means of removing it from the map. So now we have this back element, but I don't know how to remove it from the map because I have no reference to the key on that element. So we're going to need to store the key for the map on this element rather than just the value. I don't think this has an inbuilt way of storing. So what I'm tempted to do is to make a new type, which would be a cache element, or a cache map element, which will go on the map, and this will be an element which is a pointer to our list element. And it will also have the key here. Yeah. And what this will do is then free up the element node to have the key as a back reference. This isn't happy because we need to put it here too. And this does need to also have list of listing. What's the problem with this? Yeah, so sorry, this is a list.element and it's a pointer. Okay. Yeah. Okay, so what's the problem with this? Oh no, sorry, this doesn't need to go here. So the LRU cache now has one of these rather than point directly. Okay, so now we have the map, which each contains a data structure, which includes it should contain the, value. So the map is maps to a struct now, which gives us the element and the value. And the element then is now free. It doesn't need to store the value. It can just store the key. So let's go back down and sort this out. So first of all, we're going to get the value rather than the element, and the element itself will be on cache map element. Yeah, so the element itself is now stored on the value, so this is a struct, and you know, we can update this too. So it doesn't point directly. Push to front. Element. Cannot use. So you know, push front. Element is type cache map. Yeah. So here we need to now, when we're setting, we're not storing the element directly. Again, we're storing the cache map element, which has the L as the element, Alex key, and the value, which is the value here. And I think the value is a string. Perfect. Yeah. So what's the problem here? L type cache map element. Yeah, so this is a V. L is defined here. Yeah, good point. This should be a pointer too, so that we can. So this should be a struct of pointers, a map of pointers, so that we can modify them directly without having to reaccess the map. So we have the V cache map element, a pointer to a cache map element, which stores the list node and value. And this is the removal. So we'll say, yeah, so this is what we'll come back to sort this in a moment. This is where we found this problem in the first place. But down here, else, we can update. It's now v.value equals value, not this, and move to front is the v.element. So that should implement all of that and make all the compiler happy again. But when we run this, we still get this problem that the UK is still present, right? And this is back to the problem we had, but now we can solve it. Where we're trying to remove it now, we get this element, and I didn't, when I set the element, let me see. So when we first set this element, we don't want to set the value anymore, we want to set the key. So now the key is present on the element. So that here, when we are trying to update it, we get one from the back. So the back element key is now backl.value. And again, we know this is safe to cast with string. We don't need to cast below because we're not storing the value here anymore, we're storing the key. So the value is going to give us the string. We're going to now remove the back element, and we also know that we can delete from the map. Yeah, that's correct. The back element key. because the element at the back, as its value, is storing the key in the map of the one that we need to remove. And hopefully, okay, we didn't. We expected Paris but got France. This seems like an error in input. Cache.set, cache.get France. Expected Paris but got. This is on line 42. So, so this looks like I've messed up here because it seems that here I'm getting the key instead of the value. So when I'm returning in the get here, yeah, we don't need to do this anymore. We need to return v.value rather than v.element.value, which is actually the key. And there you go, and it works. And just to kind of make this clearer now, let's walk through how that removal works. So if I set, if I just remove these for a moment. So here we're going to set Belgium and it's going to remove the UK. So we're going to step through to here. We can see that the length of the list is, it's been useless. We can see the length of the list is 4 and the capacity is 3. So it knows that we've got to remove one. So it's going to look at the back, and the element at the back is, if we see here, is UK. Okay, so it knows to remove the UK, and the value of this element on the list is actually the key. Okay, so the key, which is UK. So now we delete it from the list, so we're going to remove the back element from the list of least recently used, but then we need to delete it from the map. And to do that, we use the key that we established from the element. Here is UK, we delete UK from the map, and it's gone. And you can see the test passes. Yeah, so it's quite an interesting one, really, this kind of hybrid approach combining the lookup power of a map with the ordering power of a linked list and the reordering power of a linked list. And I think this is what makes it such an interesting problem, the LRU cache, and so interesting to be able to use the linked list in general, to be honest. But yeah, anyway, that's my implementation of it in Go, in constant time. I hope you enjoyed it. Thank you very much for watching. My name's Sam, and I'll see you in the next one. Till then.